What a day. Guys, I've been saving for a rainy day. So far I've managed to buy myself a rain jacket and a dinghy. Couldn't quite afford the camera cover yet, so I'm just going to wrap you up. And then, let's show you the job. I'm going to explain the job inside the van because it's absolutely tipping it down outside. First of all, welcome to my new van. It's a lot of the same equipment, but I've just laid it out a little bit differently. Milwaukee sponsorship and all that now. Got sent some nice stuff, which is very kind of them. Honestly, I'm absolutely loving it. My van is so American now, I feel like I should probably check my cholesterol. First aid kit at the back there, the Hoover, everything. And I've gone a bit pack out mad because I'm often working in areas where tool theft is a bit of a problem. I don't leave anything in here now. Anything I do leave in here is in the safe, and anything that doesn't go in the safe that's of value, like the Hoover and stuff, I put it on my little roller, not the scooter, this one, sorry, and that gets rolled off of site. Anyway, I digress. Let me show you the job. So we are going to be taking this house completely off grid. As promised, whenever I have an interesting job that I think is going to be educational, I'd get the camera out. If I don't have something that I think is worth filming, then I don't film. I stuck this in the other day, just very temporarily. It was an earth rod. We're going to be converting this house into a TT earthing system, or Terra. And if you're going off grid, you've got to do that. You can't use the supply earth, especially if that supply earth is PME. What are all of these letters? What are all these acronyms? TT, PME, SNE, TNCS? What? It's all going to make sense to you by the end of this video. Before I go into the science of it, let's actually show the practical. I'm going to stick an earth pit in here, not this one. I've got a proper one, and that way you get to see Sparky have to do some actual labour. Please don't be like a giant wasp nest behind here or something. So the distribution board is just the other side of this wall. So it's all just in there. But I need to disconnect from the supply earth. So can you tell me what earthing arrangement this is? I'll give you a minute, I'll show you the cable, and I can tell you. So this right here is TNCS, Terra Neutral Combined Separated. So it basically means that the earth for the property is going on and is joined to the supply neutral. So you see how it goes into that same terminal block there. Makes sense? Not too bad, is it? We're going to have to disconnect from this and put in our own earthing arrangement. So practically that means running a cable outside through here and connecting onto a big metal rod in the ground, as adequately demonstrated by the big metal rod in the ground there that I hammered in earlier. But I just need to very carefully drill through and into that consumer unit cupboard, so I shall do that now. Ted has one job: keep the batteries charged. There's a lot of misconceptions and things on the internet about going off-grid. I'm sure if I searched off-grid, there'd be an unlimited number of search results for people trying to tell you the science and the things behind it. But there are some really important safety principles behind it that are often skipped over, especially here in the UK with the type of earthing systems we use. And this, as you can see, is it's very jerry-rigged up. It's very much temporary, but this is a proper off-grid system. Okay, so this is 15 kVA worth of Victron inverter. You've got a 20 kVA generator, a whole load of solar going in, battery stacks here, you've got 30 kilowatt hours of battery. It's a proper setup, but what I want to go into today is the earthing system. I've come out here to get my whiteboard. You know it's going to be serious. Let me get the whiteboard. We need the pens and we need the whiteboard. Okay, righty. Let's try and explain this the best way I can. And first of all, let me preface this with, I'm not a teacher, but I'm just going to explain it as I understand it to see if that makes more sense for you. Let's get this straight. There is earthing and then there is bonding. They might use the same cable, but they're not the same thing. Earthing is about magnitude, okay? Bonding is about equipotential. You have two different types of equations, okay? So you have this one, adiabatic equation, which is what you use for earthing, and this is all going to be simple very soon. And then you have the equation you use for like supplementary bonding, something like that. The adiabatic equation is about basically making sure that the resistance is low enough of that path back that the magnitude of fault current will blow your protective devices and you will achieve disconnection times. Bonding is about equipotential, making sure the old principle of the pipe, making sure that you've not got more on one side, pressure-wise, than on the other side. Say this was live because there was a fault and that became live, and I went to go touch another piece of metalwork simultaneously, I'm not going to get zapped, basically, or more likely that between the inverter or something. So UO is just fancy talk for your RMS value to earth, so 230 volts in this scenario. RB is the resistance of you as a human, and that is measured. You don't want to know how we've got these figures. Google, it's a very dark place. That is the resistance between hand to hand in this scenario, and that is measured in the IET guidance note 5 as 1000 ohms. RX is your measured resistance in the circuit, and IB is the design current. In this scenario, it needs to be below 10 milliamps before it's seen as harmful to health and life. So that means, with that being the case, this figure here needs to be over 22,000 ohms. If it's over that, you're safe. If it's under that, then you're going to start getting this figure here higher. So you want this to be below 0.01 amps, basically, or 10 milliamps. To make this make more sense, right, let me draw it out for you. If you've got your transformer here, yeah, your supply transformer, and you've got your consumer unit, and then you've got your load. I don't know, it can be a heater, it can be whatever you want it to be. You're going to have your live or line conductor, if you're a complete dork, coming in here. Your neutral, oh, look at these lovely pre-harmonized colors. Your neutral coming off, and then I'm so bad at drawing. And then obviously goes through your main switch or RCD or whatever into a breaker or an RCBO or whatever, and off out to the load. On the other end of the load, you can have your neutral, which is going to connect on, come off and back, and that's just going to go into your neutral bar, which effectively just goes into that switch. So in the normal operation of a circuit, when everything's all hunky-dory and everything works as it should, that is what the circuit looks like. So do you need an earth? No, you don't. You don't need an earth to make the circuit to work. Do you need bonding? No, you don't need bonding to make the circuit work, not at all. The circuit will work just fine without it, until it doesn't. Until something goes wrong, and then you're dead. If you enjoy your attachment to life, then I recommend you do use an earth. Quick scenario to throw at you. This thing's full of water, this thing has a fault, whatever. That casing now, let's draw some danger lines around it. Oh, I wish I had yellow. Please donate to my channel or become a member so I can buy a yellow marker. That's now live. And that could be sitting there live for ages. It could be like that for months, years even. Who's going to know? Who's going to stop you? Until poor little Timmy. Oh, Timmy's so cute. If only you could see him. He's just started, what's something cute? I don't know, whatever you're going to say is going to sound creepy now. He's just started losing that lisp of his, bless him. He comes up and says, "Oh, Mummy, let me turn the heater on for you. Oh, while I'm standing on this lovely earthed ground, earth, same thing, yeah? Here, let me go, don't touch it, Timmy." Too late, he touches it. That fault current now, because he is standing on the ground, the transformer is earthed, the neutral point of a transformer is connected to earth, that fault current is going to, and Timmy was, that doesn't make any sense, but Timmy is now dead, and that's really sad, and that's because you didn't have an earth. There's nowhere for that fault current to go, and that is serious. It's really serious. It's no joke, as much as I might have just made it out to be one. So what do we do to resolve this? Well, we have protective devices. These protective devices trip and blow. Fuses blow. Adiabatic equation. This metal casing is connected to earth. That's why we have it. That goes out to main earthing terminal, and in this scenario, which I'm going to be showing you shortly, out to an earth rod. Let's replay this situation. The fault is not there. All of a sudden, it's there, but now there's an earth path. That casing now is live. We want to make sure that this path here is the tastiest path, not little Timmy. He's got so much life ahead of him. He's one of these cool kids that wears his baseball cap backwards, but not to be rebellious. He goes to touch that, little Timmy, oh, look at the smile on his face, but he's safe because his electrician installed protection. He installed an RCBO here and that. Timmy's little heart, we want to make sure that it's never going to see more than 30 milliamps of fault current. The fault path now looks like this, okay? Current coming in, through the metallic casing and down here. This right here is the tastiest route for the electricity, the path of least resistance for that to surrender itself back to the transformer, completing that circuit. And that right there, my friends, is an earth fault loop. Ring any bells? Earth fault loop impedance testing, etc. The measurement of that fault loop there is the impedance, measured impedance of that circuit, of the system, that whole system's impedance. So when you plug in your little tester and do a ZS, like this, tester set to loop for earth fault loop impedance, my socket tester plugged in, push the test button, and that's my system impedance. That reading that you're taking is this whole number here. And when you do a R1 plus R2, like this, you know, where you join these two together and take your resistance readings of the live and earth, you are measuring half of that earth fault loop. You're adding these two values together and you're getting that fault loop. When you do a ZE, which looks like this, loop high, and we're testing between the supply line and the supply earth with a disconnected main earth and main switch switched off. What you're actually doing is you're measuring this plus this, effectively. You're measuring that return path, that half, which is why when you see the equation, ZS is equal to ZE plus R1 plus R2. Does that make more sense now? I hope it does, because otherwise it's been rabbiting on for absolutely nothing. You're going to be saving Timmy's life. 30 milliamps, again, oh, that's dark. If you really want to look into how we know how much electrical current the body can take before things go wrong, I recommend you Google that in your own time with caution, because it's not very nice. I think that'll do for now. Let's get to it. My own I haven't got a TED. I don't mind. I like his company, but I don't really need him for the heavy lifting or anything anymore. I've started using Peloton. Not sponsored. Paid for it. I'm still dubious. I'm still on my free trial, but I quite like it. It feels a bit like Dora the Explorer for fat people. Putting myself in that boat. Like, I was doing a tour of Puerto Rico last night on my Peloton, right? And it's like, over here we have my favorite taco stand, and over there I have my favorite place to buy whatever food it is. And it's, I don't know, it's like, it's nice, keeps you entertained, takes your mind off the exercise. If I end up absolutely shredded, you can thank the lovely Senorita from Peloton. Okay, so the distribution board is on the other side of this wall. It's at a very scary angle. We have found that angle. I think it's approximately this angle. Okay, I'm not out that side, so I must be in the wall. It just feels very easy. Can I do a rewards acceptance speech for Angle Driller of the Year? That right there is my drill bit. Precisely where we wanted it to be. So we're connected onto this. You see how it combines there, the neutral and earth? We can't use that because we don't want to be sending any of our naughty stuff when we're in island mode back down the neutral. So we're going to take this earth out, completely disconnect from the supply earth, and we're going to run a cable from that metal rod right there, which I installed the other day. It's about 2.5 meters deep, through the wall, through that perfectly drilled hole, as found by this fabulous angle finder, out and into there. This is our earth rod, and do you know what? A lot of people, especially in colleges and things, haven't seen one of these in the UK because they're not all that common, especially in the city. That is basically a 2.5 meter lump of copper that I've hammered into the ground, and then this is going to go around that. I just need to dig it down to that level, then this will sit on top. So you quite often see these in the streets, and they're little earth rod inspection pits. I'll go grab a pickaxe or something and we'll get digging. This is tricky. Good job I'm in really good shape now. Well, I'm not yet, but I'm on the journey to it. Oh mate, that is bang on. Okay, that's the the hard bit done. Let's get the cable in. I've already terminated this, ready to go. This is crimped and heat shrunk. Shrank. Welcome to England, right? It was absolutely chucking it down earlier. Like, this t-shirt is absolutely soaked. My trousers are absolutely soaked, but now the sun is shining and the birds are singing, so I cannot complain. Nice little thought. It's always a blue sky above the clouds. Right, so inside here, I've connected that up. It goes along, up through this boxing into here, where I just need to fix it back. Just stapled it along there for now. Oh dear, that's not going to do, is it? That needs a bit of straightening up. Stapled it along, up, and now it's ready to test. I'm going to be doing a whole video on this off-grid setup, but you're going to have to subscribe if you want to see that, because that's coming soon. So this is the TT earth rod, do you remember? No, not that type of TT. Terra, earth. So that's referring to, we're connecting the distributor's earth to our earth spike. And we're going to disconnect theirs and get a ZE reading. Do you remember where that comes in? The external impedance. And the value I'm looking for, the recommended value for this is 100 ohms. We want this to be below 100 ohms. There's a magic number, okay? In the electrical world, 50 volts is, I don't know why I did that, parentheses, 50 volts is considered to be safe touch voltage on AC. Anything below that, 51 volts, anything below that, you're safe. So if you know that you've got a 30 milliamp RCD, which we will have with the earth rod, the maximum allowable resistance with an earth rod is 1667 ohms. Oh, you thought you got away from the classroom, but you're wrong. Why am I so concerned about making sure my number is below that? 1667, okay? 1667 and not the beer. The reason for that is, if we remember the old Ohm's law, yeah? VIR, volts, amps, resistance. What's considered the safe touch voltage for electricity is 50 volts. 51 volts, you're dead. 49 volts, you're fine. Do you remember Timmy? He's all right with that. Anything over that, you've killed him. If we know that we've got a 30 milliamp RCD, then we know our current is 0.03. We know that we want to get 50 volts. Then that means our resistance will equal, pause, put it in your calculator. That is right. So that will come to 1667 ohms. That is why that reading that we're taking there has to be below that, because we're trying to get below 50 volts safe touch voltage. Right then, so let's do a ZE test. Get to the main tails coming in. So I've got my tester set to loop high. The Q-Tech, which this tester is a budget tester in the terms of how much it costs compared to others, but I absolutely love it. I have used various brands. I've had Flukes, Megas, etc., but I just find this does the job. It's simple, it's easy to read, colour display. Need I say more? Right then, so we're going to test between the outgoing live back to the transformer, or incoming live to the property line, and the earth rod, and we're getting a reading of 4.55 ohms. So that is well below our 100 ohm recommended permissible value. I know there are parallel paths connected, but none of them are really going to be relevant in this because I'm not testing against the neutral. So I'm pretty happy with that reading. So that's the earth rod done. Okay, so I've disconnected the PME earth, and I've just double checked with all the bonding conductors, with everything in, I'm getting a reading of 0.62. So that is, it's not really a true ZE value because I've got a lot of parallel paths, as in I've got my water bonding, my gas bonding, and all the rest of it connected in. But that is also kind of my real world reading. That's not the reading that I put on the certificate. The one I put on the certificate is the 4.6 ohms or whatever it was, because that is the official ZE. But it's nice to know that in practice, with everything actually connected, I'm getting 0.62 ohms. So yeah, pretty happy about that. Okay, so we're back in the garage. The next part of the quest, really, like what we've been talking about, is the bonding. So how would I decide whether to supplementary bond this or not? Within a house, there are 3 requirements that are necessary for you to not have to bond something. Supplementary bonding. Do you remember the days of bonding aluminium frame windows, bonding your radiators, all the rest of it? That's not necessary anymore, really, generally in a house. But in this environment, I've decided I am going to use some supplementary bonding, because I kind of consider this a bit of a special location, really, with everything going on. So many generators as well. Like, we've got this generating power, we've got that generating power, we've got mains coming in, we've got a big old diesel tank, all the rest of it. So that will be the plan, and we're going to have like over 100 kilowatt hours of storage in here. So there's 3 requirements. I want you to go find those 3 requirements and comment them below. I'll give you the first one. Okay, the first one is that you have mains bonding in place, so bonding on your water, gas, structural work. The rest of it, you tell me the other 2 reasons below. So to decide what's actually going to be bonded, there'd be the equation that I mentioned earlier. So we need to make sure that the Rx, or the resistance between what I can touch here and here, is over 22,000 ohms, or 22 kilo ohms. So I'll get my test meter, I'll measure between there, and if that resistance is below that value, then has to be supplementary bonded. I think, to be honest with you, in here, with how close everything is, and on a potentially damp floor, because we are outside with a tin roof, I'm just going to bond everything. But at least now you know the science and the theory behind it. And I hope you're looking forward to this, because just have a look around. This is what is up to come on this channel. This is all the things that you could learn if you just subscribe. See you next time.